Last time was starting the discussion of analytic sets, and it wasn't really going into any of the actual definitions that we used, but it was trying to give an overview of what the definition should look like and what kind of examples it should accommodate. And so today I want to go a bit more into like the actual definition. So I want to talk about analytic stacks. But something that kind of dictates how we set up this definition is actually a series of 6 functions. So I'll be one of them. Okay. So last time we saw some motivation for making a definition of the sort. Analytic stacks. One could be some category just sheets. On the category of analytic rings. And this definition and module of issues of set theory that does kind of explain how one should address the other thought. Actually, now implicitly these will be like sheets with infinity group as animal, whatever we call them. And then in that series of sheets, there are some other subtleties related to so-called hybrid sheets versus hybrid sheets. But I will probably also say something at the end of this lecture, but it's also more clear. So we would like to define our geometric objects by studying the grids, which gives us our basic building blocks, the MPIM spaces, and then specifying some broken topology which tell us how we are going to glue them. And so the key question is like which broken topology?
The sound transmission is not very good here. We cannot. It's hard to identify what you say, but I don't know what's the problem. But
the problem is that I didn't put on the microphone. So say thanks for catching that, sir. Sorry, do you hear me better now? Yes, no, maybe?
Now it seems natural, yes.
Okay. Sorry. Yeah, so I said that I want to talk about analytic stacks and 6 functors, and that last time we saw some motivation that we should try maybe to define our category of geometric objects, these analytic stacks, by starting with the affine analytic spaces corresponding to analytic rings as basic building blocks, and then specifying some broken topology which tells us how we are allowed to glue them. In setting up the precise details of this, there are some set theoretic issues related to the fact that this is a large category and also some consider small sheaves. And other technical issues that will arise is that we are really considering sheaves of infinity groupoids, or what we call sheaves of anima here. And then there's an issue of sheaves versus hypersheaves. And we will actually, at the end, consider something strictly in between, but okay, let me not get into this. But the key question really is which broken topology to put on this. So, there was some motivation for this definition, and lots of examples were mentioned that we will be taking up again once we have the proper definition of the category. All right. Before I get there, let me remark that what we're doing here is kind of very, very close. So at the beginning of the course, we did something extremely similar. We defined condensed sets or light condensed sets if you can put or not put light on both sides of this equation. Sheaves on the category of profinite sets, or if you want profinite sets, I was thinking of Boolean algebras. And so there we were playing a similar game that we had some basic objects that we start with, some profinite sets, and then we were building a larger category by somehow allowing ourselves to glue them in a certain way. And the gluing that we allowed was specified in the Grothendieck topology that we chose. And what then we chose was rather general Grothendieck topology, allowing all, in particular, all surjective maps of profinite sets. And something we are now repeating this game with a much more broad class of basic geometric objects corresponding to these analytic rings. And these are somehow able to model all sorts of different geometries. They can model sorts of just algebraic geometry. They can model some p-adic geometry, some adic geometry, some complex geometry, whatever. And all these different kinds of geometry are somehow built. You can put them together in this world of analytic stacks and build spaces out of all of these things together, right? So something that's done in some areas of math is also, I don't know, maybe consider instead of some nasty class of topological space like profinite sets, you would rather start with some nice class like smooth manifolds, and then play these games and with a different logical space or something like this. But all of these would be part of this world of analytic stacks now. All right, so the key question is which growth is so here are some things that we want. Figure out that. So the most important invariant. So if you have a triangle mod A, an analytic ring, and let me just stress that by this I really mean analytic animated rings. Again, most practical examples I will not have this animated structure, but the general formalism works much better if you allow these things in your formalism. So whenever you have such a thing, then the primary invariant that you're interested in is its derived category of complete modules. Recall that this was defined as a full subcategory of the derived category of the condensed A triangle modules, such that all the homology groups are complete. And okay, so this is a primary invariant, and we want that somehow A maps to V of A is a sheaf. But it's this derived level. The only sensible way to phrase this is that it's a sheaf of infinity category. So we actually need to treat from now on always this as an infinity category. So let's send with something we want. We want that this. So this already means that for any analytic stack X, we will be able to define the rough category of quasi-current sheaves on XY descent. So it's just a limit over D of A over all A mapping to X. So that's good. But actually, we want something slightly more. And this is some of this business with the 6 functors. So we also want that x equal to d of x equal to one of the 6 functor form. So let me say a little bit about what this is. So there are 6 functors. There is always a tensor, which has some kind of right adjoint, which is an internal Hom. Then there is a pullback, which has a right adjoint, which is put forward. And then, and these will be things we already have. And then there will be 2 more that we would like to have. We would have to like a floor streak functor and a right adjoint. So always this one is left. What's the structure here? So each d of x should have a tensor, i.e. be a symmetric monoidal. And then whenever you have a tensor, you can ask for an internal Hom object, which has this usual adjunction to the tensor. And if such internal Homs exist, it's called a closed symmetric monoidal structure. Then whenever you have a map f from y to x, there should be a pullback functor. It should be able to pullback sheet. And this should actually be compatible with the tensor product. It should be a tensor functor. And this should have a right adjoint. So also this is something we just get automatically because like when you have a morphism of rings, you can base change modules, and also then this induces the same functoriality on d of x. And it's the way this formalism works, this will automatically, like if you tensor modules, this will be compatible with space change. So this is a structure that we definitely already have. And yeah. But then there are these lower street functors, not the sheet functors. And so this is a more delicate kind of structure, which only exists for certain maps, for certain f from y to x. We want want a functor f lower street from f1. so-called homologous compact support. And this should satisfy two properties. One is the base change. So whenever you have your morphism Y, and you have any base change of this, so first of all, the base change should be again in the class where this f log freak is defined. But secondly, there should be like taking first f lower freak and then pulling back. This should be naturally the same as first pulling back and then taking the lower freak. And another thing that should satisfy is a projection formula isomorphism. That for A and B of X, and B and B of Y, so somehow you're trying to say how these lower street functors, they interact with the existing structure. And so the first thing is that with the pullback, they should just commute in this sense. And then with the tensor, you have the following property that whenever you have A and B, then take f lower 3 of f upper star A and the B, which should mean the same thing as A and this. So this is a kind of structure that arises in a lot of different contexts in mathematics. The most classical is in some sense, if you take some nice category of topological spaces, something like locally compact cluster spaces, and find a suitable version of the right category, then this has a structure actually for all morphisms. Where this f lower trig is literally cohomology with compact support. So you're looking at the functor of sections which have compact support, and then you can derive that functor. This is what this f lower trig is in that setting. Actually, the first time this was developed was, however, not for this case, but it was for Étale module schemes, I think, for Grothendieck. But then it was realized that there's, I don't know, you can also do this for D modules, and you can also, I don't know, there's lots of different settings where you can do this. One setting where it was, however, not so much developed is a setting where now it's some kind of coherent settings or quasi-coherent setting, where usually you do not really have a notion of cohomology, coherent cohomology with compact support. There is this appendix of Deligne to Hartshorn's residues and duality, where he kind of says that you can develop some such formalism, but it's, and there are a few papers here and there which talk about coherent cohomology with compact support, but it's not really a theory that is used much, I don't think. But actually, our setting naturally will include a theory of coherent cohomology with compact support that behaves rather well, and we do absolutely want to have it. Right. But before going on, maybe let me make a remark, because I think Gabor will complain in a second, that there is a completely imprecise definition here of what a six-functor formalism is, because when I write this isomorphism here, there is no natural comparison with them between the two. These are just two random functors. but they should naturally be identified. So you have to supply this isomorphism. But once you start supplying this isomorphism, then you run into trouble because now, I don't know, you can like base change twice. And then there's a comparison isomorphism here, a comparison isomorphism here, and one for the composite. Well, of course, you would hope that they commute, but then you start to wonder how many different such things you can write down and which kind of compatibilities you have to enforce. And I think for a while it was some kind of open question what a really good and minimal way to encode all the data is that is present in a six-functor formalism. And there has been work by Liu Zhang where they do this in the world of like artist stacks. And there's been work of Gates-Gerrig Rosenblum where they're actually more interested in coherent cohomology, although their functors have different names, and so they don't really talk about complex support cohomology at all. But also in coherent settings, they set up some kind of notion of what such a six-functor formalism is. That treatment is, however, infinity two categorical, and so that's difficult. And then, like Lucas Mann may be really isolated the key structure that you need. So yeah. So yeah, there is a go. Infinity categorical notions. Of such an abstract six-functor formalism. And this is something that I gave a course about last winter. And let me simply refer you there. Right. And so, but something, some moral that I also personally was taking away from this course is that if your desiderata are that you really just want the six-functor formalism, then this kind of dictates everything, including the Grothendieck topology. Including in quotation marks, correct. All right, so right, so yeah, before we starting the discussion, in our specific case, then recall the usual definition of such an Floor street functor. Like usually. So we do this by specifying two collections of morphisms. So there's a class of proper morphisms. And here, f lower streak will actually be just f lower star. But if you want to make this definition, you better check that it satisfies the properties that that an f lower streak should satisfy. So need a proper base thing. And the projection formula indicates proper morphisms. To hold. But this time, you're in a slightly better situation because when you take this to be f lower star, then there's actually always a natural base change transformation. And so then here, I'm not supplying data, I'm just asking conditions. So when you want to declare the morphism to be proper, and so f lower streak to be f lower star, there's something you can simply check whether it does the natural base change transformation is an isomorphism in the case of this morphism F. And similarly, for the projection formula, there is a natural map from here to here, if you think about it, when this is F lower star. So these are just conditions. There's no data supply. Okay, so there's a class of proper morphisms that uses, and then there is a class of open emergence. Where instead you're asking that f lower streak, I mean, here he asked that it's a right adjoint to pullback. For open emergence, he asked that it's a left adjoint to pullback. And again, you need to check that this is a reasonable definition, so you need to check that it satisfies base change and projection formula. But this time again, also if it's a left adjoint, there is a natural comparison map between these two things, this time going in the other direction. And you ask that these things are satisfied. So again, base change and projection formula are conditions. Okay. And then the general maps F that are allowed, or I would call them streakable. So these are the ones that are for which this lower streak function is defined. They're taken to be the composites of an open emergence and a proper map. So we have an open emergence, let's call it J, proper map F bar. So the idea is that these maps that you can choose are the ones which you can somewhat compactify, like that. And then you want to declare that the F lower streak is the composite of the J lower streaks. Where the proper case F lower streak is F lower star. So here's this left adjoint of pullback, here's the right adjoint of pullback. This definition comes a priori with a really big caveat that when you write down this as a definition, it's not really a definition because you chose the compactification. In general, there are many, many possible ways to compactify. And so you have to show that this definition is independent of the choices canonically, because I mean, you really want to get infinite categorical structure, so you don't just need to show that some are unique up to isomorphism, but even the isomorphism is unique up to higher isomorphism, and so on and so on and so on and so on. So this sounds like a real pain, but fortunately, there is a theorem that was essentially proved by Liu and Zheng, and then like slightly streamlined in its formulation by Lucas Mann, that under really minimalistic assumptions, on the classes of proper maps, open emergence, and some of the general shriekeable maps. So essentially just what I said, except like for example, you want that a composite of shriekable maps is still shriekable. So you need that a composite of two such maps, again, can be compactified. So there are some very small assumptions, but they're extremely minimalistic. The theorem is that then you can always produce such an abstract thing functor formalism, such an infinity categorical set. It's determined. And abstract this one. The precise theorem is in these lecture notes on these functors, or in Lucas Mann's thesis, or whatever. In particular, these assumptions include no condition whatsoever on the uniqueness of compactifications.
So do you assume something like the two compactifications can be dominated by a third one?
No.
No?
No.
Is it a question?
There's a question in the chat. I mean, these are the kind of things you want to do with this. Yeah. So the question in the chat is, using this functor formalism can be derived from Riemann-Roch formulas, finiteness of homology, characteristic classes, index theorems for analytic states. Yes, that's the kind of things we hope to do with this stuff. Right. So Gabo's question was about whether I should assume that two compactifications can be dominated by a third. Well, there is something that follows from the mere existence of compactifications of morphisms. Right. So if you have two, then you can take a fiber product, which is a third thing that's still, this match should still be. So it might be that a little bit follows, but it's not explicitly mentioned that you have to check something like this. See, but you need to know that all maps which are shriekable are such composites. But you just ask for each shriekable map, you just need to produce one compactification. All right. Right. So now we apply these general ideas to our setting. So we start with a category. Or infinity category. C, which is analytic rings up. And we call them affine analytic sets, if we want, or affine analytic spaces. And we will generally call an object in here the analytic spectrum of some A. But the unspec doesn't, I mean, it's just a symbol, yeah. There is no topological space now for chain. It's just a symbol to say we're thinking of it now as a geometric object, passing to the opposite here. All right. And so we need to figure out which morphism here should be proper, which should be open emergence. And at this point, we should forget any preconceived notions of what a proper morphism in algebraic geometry is and really just look at what the formalism tells us, okay? Definition. And that's F, transpect E, transpect A. So in other words, the map of analytic rings from A to B is proper. So usually you would expect that this is virtually never the case, or only for finite maps. Now it will be a rather general thing, okay? So this notion of properness is different from the usual one you use in algebraic geometry. If Forster from D of D to D of A right, so this is simply the forgetful functor, right? You have a morphism of rings from A to B, so in particular any B module is an A module. That's what the Forster is. If this satisfies the projection formula. A priori, I should ask for more, like for base change and so on. It turns out that if this happens, then all the other good things you want are also true. So. So to analyze this notion of properness, let me recall. So if you have such a map, this will always factor in the following way. So you can always first take this thing. So this is a tensor product of analytic rings that we described in a second. So what is this? This is some LB triangle and the class of all those B triangle modules such that if you forget the B module structure down to an A module structure, so a triangle module structure, this is complete in the sense of A. And so such things we call an induced analytic ring structure.
So do you implicitly work with animated ring and take modules over pi 0 as the category?
Yes. Yeah. Yes. Okay, let me use Dustin's notation. So he was always talking about, in the animated context, he was talking about this pair. He was talking about a pair of a animated condensed ring, light condensed ring, and a subcategory of the connected derived category, satisfying some conditions. And then I could just as well say that. And of course, working in the animated context, the standard product is implicitly derived too. Right, so whenever you have any analytic ring and just an animated algebra over the underlying animated condensed algebra here, then you can always endow this one with an analytic ring structure where completeness is just completeness when you restrict the reaction to this subring. Right, so whenever you have any map of analytic rings, there's an induced one, and then there is some kind of localization where you're just taking the same ring, but then doing a further completion. Okay. Yeah. So you always have this factorization. And this, it turns out, geometrically precisely corresponds to the process of compactifications, basically. Except this may or may not be an open emergent. But these induced analytic ring structures, they are precisely proper maps. Okay, so here's a proposition. As above, it's proper if and only if B is the induced analytic ring structure from A.
That statement is saying that the localization is an isomorphism.
Right. Yeah. The second vector is an isomorphism. Maybe before going there, the only reason this it all seems like, in particular, if you if you embed usual algebraic rings, like commutative rings, into this condensed setting, then you would do this probably by choosing the trivial analytic ring structure, and then any map of commutative rings in usual algebraic geometry will be declared to be proper, which seems very strange. The only reason to think that all sensible to me is actually because this did seem familiar from Huber's Edding spaces. So in the theory of Huber's Edding spaces. So yeah, so this matches Huber's notion of properties when applied to things which are the central image of the Huber pair, which sit inside an Yeah, so in Huber's theory, there's always this A plus. And if you have a map of phenolites where the A plus upstairs is like the smallest possible thing it can be determined by the A plus downstairs, and this is something he calls already proper. And turns out that it satisfies also in the Tal cohomology all the good properties that the proper map should satisfy, like proper base change and so on.
Do you take here analytic Huber pairs or your adic maps or
implicitly I might be thinking about the, like, let me say take just so that I'm completely confident. Yeah. All right. Proof. Okay, so what does a projection formula say? For all n v of A, and n v of B. I want to say ask whether lower star at upper star M tender over B with N. It's the same thing as M tender A lower star N. So both sides here are A modules. Okay, so what does this really say here? Sorry, what should I do? So what you're doing here is base changing A M from A to B. This is what F upper star is, and then you're tendering over B with N. And the question was the same thing as tendering. And this seems like it should obviously be true because you should be able to cancel. But now you have to be a little bit careful about precise meaning of symbols.
In the inducing structure, you want the restriction of that to a triangle to be inside some particular.
Yeah. Absolutely. Thanks. So okay, so let's analyze this. So if P has the induced analytic structure, then all tensors can be understood to be tensors in D of A, or like a relative to the broken D of A, and then just checks out. So this is already one direction. But let's say in the opposite case, let's assume if A triangle is B triangle, then base changing to B is just some sort of completion. With respect to the analytic ring structure of B. And let's even forget the n. Like even if n is just p, then like take n to be just p triangle. Oh, like the underlying thing. Which is a triangle. Then on neither on the left nor on the right, this tensor does anything, right? You're just tensing with a unit. So then we get that m tensor AB must be equal to B to M. This is what this formula says. So in other words, the further completion shouldn't actually do anything, right? I.e. M was already complete. And so this says that if the A triangle is the B triangle and the map is proper in satisfying the projection formula, then actually the analytic rings must be the same. All right, and so so in general, you just have to do the same argument slightly more carefully. Namely, I mean, in general, you can just take n equal to b. Then the left-hand side becomes the base change from n from A to B in the sense of analytic rings. But the right-hand side is a base change of n from A to B purely in the sense of complete A modules. And so that these agree is precisely the assertion that it's induced in a ring structure. So you get this equation where the tensors have these meanings, and that they agree that the base change in the sense of analytic rings is just the tensor in D of A is precisely saying that this must be an induced analytic ring structure. Because for the induced analytic ring structure, that's precisely how you compute the base change. So in general, when you compute the base change for map of analytic rings, at first you do the base change for the induced analytic ring structure, so you do this. But then afterwards, you would still have to make it complete as a B module. But here it's saying that you don't actually have to do it. All right. Okay. And the corollary of this, there was a question? Do we have anything? I'm not sure what the question like. like the map from in usual algebraic geometry, the map from the affine lines to a point is not proper. But if you like pass through this word of analytic geometry, then it's counted as a proper map here. Because it satisfies the projection formula, it will also satisfy proper base change and so on. I mean, actually, the classical base change theorems and for querying for homogeneous algebraic geometry, so you don't need to ask for properness, you only need to ask for a QCQS map. All right. So, and Dustin would be able to give to really sell you why this is good. Let me know. Right. So corollary. It's just a class of proper map. It's stable on the base change. And proper base change and the projection formula. Proper base change. So this is same on the base change, or it tells you that after any base change, still the projection formula holds, but also proper base change holds. And hey, this is a simple check. If you have an induced analytic ring structure, then you can just unravel what all the symbols mean. It comes out right. All right, so let's get to the class of open emergence. And again, I ask you to forget any preconceived notion of what an open emergence in algebraic geometry is. It's an open emergence. I will give examples in a second. Let me actually call it J, just for psychological comfort. It's an open emergent if the fallback map, like base change of modules, admits a left adjoint. In 3, satisfying the projection formula. So let me give first a non-example and then an example. So non-example is any open immersion in algebraic geometry that's not also a closed immersion. So open and closed immersions, okay, I don't know. They're kind of stupid, but like if you take, I don't know, the GM Z adjoint T plus minus 1 inside of some Z adjoint T with like trivial analytic ring structure, this is not an open immersion because I mean usually in algebraic geometry, callback, like tensing of modules virtually never commutes with any infinite products, right? If you want the left adjoint, this should mean that the pullback should commute with products, but it just doesn't. All right. But there is a way using some adic spaces and like relative solid ring structures. So there's a different way to pass from algebraic geometry to analytic spaces using solid analytic ring structures. And if you do that, then actually it is okay. Then open emergence go to open emergence. So here's the key example. If you take like here's one example. The unstack of Z adjoint P plus minus 1 solid. The unstack this would be an example. Or also, and sometimes more primitive because this one can be realized now as a base change of this one. Not quite, but essentially. Like the key thing to know is that if you take like Z joint T solid and embed this into the induced one, Z joint Z solid, this is open. This is something that already came up in a remark once somewhere in the lectures, but that I want to spend a little bit of time on now again. I forgot something in the definition. I want it to be an open inversion, not just for which I should pass that this left adjoint should be fully faced. It's equivalent to the right adjoint, which always exists. The J lower star to be fully fixed. So basically, this should be some kind of localization here. Right, so why is that true? So what is J upper star in the second example? J upper star of some modulo n is the internal home from or let's say if I take a module on the base, pull it back, and then push down again, so that's somehow the completion. That's a key solidification. Of an N, which is in the garage category of the joint T. And Dustin showed how to compute this in terms of this R home from this funny object. And so this thing should receive a map from N. So the R home here is over T joint T. And indeed, I mean, this complex it maps to Z joint T in degree 0. So this is in degree 0, so this is homological degree -1. Homological degree -1. Homological degree 1. So this maps to Z joint T in degree 0, which on R homes gives me a map back, which is the junction map. I think, yeah, if you look back at Dustin's lecture on like certification of a Z joint T, this is the formula he gave. And this means that actually if you tangent with this object, then this would become the left adjoint. So it is M tender. And in this one structure. And here, these brackets mean some other complex. And so this means that this left adjoint J-lower streak exists on the image of J upper star, but J upper star is essentially surjective, so it exists. It also says that like this left adjoint is given by tendering with some module, which is exactly what you need to check that it actually satisfies the projection function. All right. So why is this reasonable? Why does this have anything to do with the intuitive idea that these lower streak functors, there should be some kind of cohomology with compact support? So in particular, the lower streak like of the structure sheaf of unspec, i.e. the upper streak of some of the Z and T. So this should be like the compactly supported coherent cohomology in some sense of the affine line. Well, what should it take to somehow give a like a compactly supported thing? It should give it, yeah, if you want a function on your thing, which has compact support should vanish near infinity. So giving a function, well, that's an element in Z adjoint T. And now you want to say that it vanishes at infinity. But like at infinity, you somehow get functions near infinity are these Laurent series in T inverse. And so you would like to take functions that vanish near infinity, so that lie in the kernel of this map. Unfortunately, like any polynomial function is determined by what it does near infinity. So this map is injective. But as a complex, it is still a reasonable thing to do. And you have a co-kernel, which is non-trivial, and some nice. It's actually just a product of Z's, so it's like a compact object in solid Z modules. And so the key thing making this work here is that we get some such localization with its properties. And particularly, like the key thing you need to check when you want to check that, for example, this is what the completion does and so on, is that zero completion T inverse is an idempotent algebra. In like category. So it's an algebra object, and if you tensor it with itself, it stays itself. All right, and this is in fact a general description of these open emergence. So given some x like A, the open emergence J from some Y into X are equivalent, or the category of such, equivalent to either equivalent or anti-equivalent, I'm not sure now right now, to idempotent commutative algebras. I don't know, it's called C. Or, let me call it C. In P of A. Not all of them, but those such that the internal home from C 55.1 preserves some connectivity assumption. So here J maps to the following. So you can take J Loy freak of the unit, and this will always map back to the unit, and the cone of that map. This you can check is always an idempotent algebra. So it always comes. So what is it? So to supply an idempotent algebra, you actually have to only supply little data. You only have to supply the unit, and then you just have to check that when you take this unit and tensor it with C, it becomes an isomorphism. But if you take this map and tensor it with C again, then well, it's some simple matter of using the projection formula for J Loy streak to see that nothing changes. Like the key here is that if you take J Loy streak of 1 and tensor it with J Loy streak of 1, the J Loy streak of 1 tensor J alpha star of 1. But it's just J Loy streak of 1. So also J Loy streak of 1, it would be so it's also equivalent to idempotent coalgebras if you want. So J Loy streak of the unit would always be an idempotent coalgebra, but I don't like to talk about coalgebras so much, and it turns out that they are anyways canonically equivalent to idempotent algebras via this funny procedure of taking the cone to the unit. Sorry, there's something else I forgot. Such that this functor preserves all pole limits. And and this is somehow a compact object here. So that's why this works.
So how is that one map to that? How does the one map to that?
Well, it's a cone, right? So 1 just maps to the cone, right? If you have a cone from X to Y, then always Y maps into the cone, right? And whenever I have object in the right category, there's always natural maps from Y to the cone from X to Y. Right? I mean, there's always a triangle, X to Y, alpha. It's just this thing. Sorry. Right. Right. Let me just say a few words. The projection formula implies that J lowest freak, J upper star of any module M is really just J lowest freak of the unit and the rest. And this here is the central field thing. And so this means that this thing is completely determined by right, and so this means that the right adjoint this is actually just given by the right adjoint. This is functor, so it's actually just the internal home from J lowest because of unit up towards that. Right, so the left adjoint to tensoring with some object is our home from that reference. And so we know that the completion is really just given like this. And so this means that, yeah, like in particular, this new analytic degree structure is completely determined by this object. And then you just have to specify, or equivalently by this cone, right? Because then you can recover it by taking the fiber from 1 to C. And then you just need to supply the conditions on this so that this completion really determines an analytic ring structure. And so for this, you need to check two things, basically, that this completion commutes with all colimits, which is one condition I just put. And the other condition is that it should preserve connectivity. And the connectivity comes down to this other condition I put. And yeah, all the other properties of analytic ring structure are kind of automatic. All right. It's just some plain formal procedure to check that. Right. So basically, when you have an open immersion, then there's always this idempotent commutative algebra, which you should think of as some commutative algebra describing a space near infinity, right? So in the sense of this open immersion, you have this open immersion, and then there's some kind of complementary closed subset determined by some algebra, which is all these functions near infinity, and these are this idempotent algebra. So that's the general idea, is that whenever you have an open immersion, then there's a complementary closed subset near infinity, which is described by some idempotent algebra, and this is this. And again, as a corollary of this, you can check that the class of open emergence is stable under base change. And this J-Lower Schwick functor commutative space. All right, so so we've isolated what we want the proper immersions, the open immersions to be, or not what we want them to be, but the formalism tells us what they are. And then someone leads us to a Schwick map. if you factor the open merged and a proper map. But we already know which proper map to take because I already told you about this canonical factorization of any morphism of analytic rings that will induce analytic rings structure and then some kind of localization. So this F, it always factors some canonical F bar. In this case, the compactification is canonical, which is nice from this induced analytic ring structure. So this thing. And so it gets this map. Let's call it J. This J always exists. This will also always have the property that J lower star is fully faithful. So the real only the condition is that here someone has this lambda joint. Satisfying the projection formula. So if J is a and come on, the interesting example, for example, here is that if you take the solid structure on 0 joint T, and that which is solid, this would satisfy this. In this case, the compactification would precisely be the one over this induced analytic. So this here is F bar, and this is with J that I just. More generally, like if you have any map of finite type algebras and take the solid, the relative solid ring structure, then these maps they will all be shrinkable. Or if you more generally, if you have like a map of Huber pairs, then being shrinkable is exactly this condition that Huber calls being of plus weakly finite type, which just means that this subring of integral elements A plus is as a ring of integral elements generated by just finitely many new elements. So Huber was defining these kind of fineness notions also for a six-functor formalism, but for a Tau homology. These were the notions in morphisms for which you could define Lorentz freak functor in his a Tau homology of analytic spaces. But now they are also the ones where you can define Lorentz freak functors in coherent homology.
Is compatibilities for proper open dimensions out there as well?
Yes. So that's the next thing. Yeah, so there is a little bit of check here. Like if you take a composite of two shrinkable maps, it's still shrinkable. That's true. Basically just by compatibility on the base chain. And then for the six-functor formalism, there's one action you have to check, which is some interaction between the lower freak and the lower star functors for open dimensions and proper maps. Again, that's very easy to check. So I didn't discuss in this lecture like all the little axioms you have to put to make the six-functor formalism work. There are some little bits to check, but each of them is like a really simple check. And so as a proposition, basically a corollary to this general construction of six-functor formalisms, you can somehow now say that, yeah, this data, like of proper maps, open inverted shrinkable maps, satisfies all the required conditions to get an abstract six-functor formalism. Get it, the name called the six-functor. X maps to D of X on our category C, which I recall was analytic ring op, or if you want that one, analytic X. So this class of trivial maps into the above class. So in the first course we gave on condensed mathematics, the aim of this was precisely to explain this in the case of like coherent cohomology. So there we sort of specialized to Edding spaces, and in fact, the ones where the underlying ring is just discrete, and we worked with these solid modules, in particular these examples, and then we discussed that there should be such a thing. We didn't actually fully construct it then, because we didn't have the required technology really to nicely set it up. But now it's really just a consequence of these general existence results for six-functor formalisms. And then it's starting from this, it's really easy to prove, and this is what's done in these notes, to prove tightness of coherent cohomology and seriality and so on and so forth. All right. Okay, so that's nice. If we get this nice theory of, in particular, you get some nice theory of complex fault coherent cohomology. But I started this lecture by wanting to define the Scholze topology. So here's a general question that I so given the six-functor formalism, and let's say d of x from some category C towards some infinity categories. Yeah, on some categories. You may want to pass to a larger category of geometric objects, which are somehow built by gluing objects in C, just like schemes built from affine schemes and so on. Or more general stacks. So you want to try to extend the six-functor formalism to sheaves on C. Sheaves of C with values in infinity group points, if you want, for what we call anima. For some notion of sheaves. And this in particular was maybe the original question that Leo and Zhang were interested in. when they wrote their paper on six functor they somehow wanted to extend from the task for multiformism from schemes to Artin stacks or higher Artin stacks, something like that. And they proved some general results about how one can go about extending such formalisms, six functor formalisms from one category to a bigger category. And then some of this was also used by Lucas Meyer in his thesis, was slightly rephrasing it. And then when I gave the scoring, I again slightly rephrased what they did. And so yeah, so in these notes of six functors, I tried to analyze this question and try to somehow pin down like what the best Grothendieck topology is. Can find such a discussion. Including the question, including the general definition of Grothendieck topology. That I called the D topology there. No, I'm actually not. Like I'm maybe not completely happy with just a very precise combination of this D topology in the most general case. It works, but it's slightly ugly at one point. But there's still a takeaway from this, so that if you want to do this extension, the takeaway is that the covers should basically be those that satisfy universal descent, what I call universal star descent, and universal free descent. And I will explain what I mean by this in just a second. Let's say a map satisfies star descent. If if x is isomorphically to the limit of the delta of p of y with its two maps to and then there's a whole simple diagram here, and I guess where this here is a pullback, and then here is P1 upper star, P2 upper star, and everywhere you put upper stars. And universal free descent just means the same after any base change. Universal star descent. And then there is a similar thing where you replace the upper star by the upper street. So a map, but then of course you need to ask that the map admits such street functors, so a streakable map. So strict descent. The same thing holds, but with the upper street. So if F admits a street functor, then any callback of it should also have street functors, so all these maps also. And again, universal street descent means authentication. There's actually a small subtlety here, which is precisely why I'm not so happy with this topology. In setting this up abstractly, I actually need to ask this. In the case of street descent, I need to ask this after base change to any pre-sheaf, which is a really awkward condition. I don't want to do that, and I don't do it now. So when I say any base change here I really just want to base change that's staying in my categories. All right, and so don't have much time, so let me just state a theorem that actually in the case we're in, actually this, like a priori you should ask for universal star descent and universal street descent, which seems like a lot to check. Actually, you need to check much less. To some extent, this is always true any six functor holders, but I think it's even slightly better here. So the theorem is that if a streakable net f from y to x in f1 analytic steps satisfies streak descent, then actually it satisfies universal streak descent and universal star descent. In fact, it satisfies something even stronger. It satisfies true descent. So if you're not thinking about, like, usually we have a ring and you think about the category of modules, but now we can go one category level higher and think about presentable stable infinity categories linear over D of A. And it turns out that asking for streak descent is equivalent to asking descent at the two categorical level, which is actually how the theorem is proved, but this is probably not what I want to do now in the last 5 minutes. One categories. So let me just end by giving the definition of the Grothendieck inequality. we endow F-analytic stacks with a broken topology. Well, generate on the one hand just by finite disjoint unions. So whenever you have an F-analytic stack that's just a disjoint union of several, then it's covered by those. This includes the empty cover of the empty set. And these Schwinger maps satisfying. So this is a rather general class of things. It's actually very, very closely related to this notion of descendability that Arthur Messi defined, which is some nice notion, nice hierarchical notion of descent. That's satisfied for virtually all faithfully flat maps, at least all those that are countably presented, which will be another motivation actually for us to at one point switch to the light condensed setting, because their things are countably, the rings are countably generated. Right. Yeah, and so particularly if we restrict to proper maps, then this condition of streak descent is precisely the condition that the map of algebras is descending. You have that working topology, and then, okay, there, like in the beginning of my lecture, I said that there are two small wrinkles, one about set theory. So again, we should look at accessible things, and for this, we should check that this broken topology has some approximation properties. That means that sheafification of something acceptable stays acceptable. The other is some hypercompleteness issues, is that we actually don't want the thing that's just sheaves on this, because also in the light condensed setting, we're actually considering hypersheaves. So we actually want to allow a certain class of hypercovers, but it's the same ideas that go into the class of hypercovers that we have out. But okay. Basically, analytic stacks will be sheaves on F-analytic stacks for this work. All right, let me stop. Questions?
What do you mean by finite disjoint?
Well, I mean, you can have, like F-analytic stacks, they have finite disjoint unions. I mean, dually, like rings have finite products. And so whenever I take such an finite disjoint union, if an F-analytic stacks, it should stay this finite disjoint union in analytic stacks, which like it's covered by the individual ones, right?
Do you require them to be oval?
No, I mean just finite disjoint union. So if I this is a cover. Whenever I is a finite set and xi are finite analytic stacks, then this is also an F-analytic stack, and it's covered by those.
So
it's similar to how, like, for profinite sets, we were like looking at all surjective maps and finite disjoint unions.
So
finite disjoint unions includes the empty disjoint union, which includes the empty cover of the empty.
So for usual schemes, affine schemes. So what are the shrinkable maps, and what are those which satisfy descent for Schrick or for star, and what is the topology? I mean,
right. So you could do the same discussion just with usual commutative rings. In that case, I would declare all my maps to be proper, all my maps of affine schemes to be proper. Seems a bit awkward, but it works. And it's actually like in this larger category of analytic things, it's actually reasonable. Anyway, so all maps of affines are shrinkable. The condition of satisfying shrink descent is precisely the condition that the map of algebras is what Messi calls descendable. Descendable maps, that's a rather general class. For example, I mean, it includes all countably presented faithfully flat maps. It also includes all quotients by nilpotent ideals. It's maybe more surprising. It also includes all H covers. So there's this Wolowski's H topology. So you have find schemes that's a cover in Wolowski's H topology that's also allowed here. Actually, when you restrict to Noetherian schemes, that's equivalent. So when Y and X are affine and Noetherian, then this satisfies this condition of descendability. I mean, of satisfying strict descent, if and only if it's a cover in Wolowski's H topology.
Do you mean V topology? You have the H topology with Frank represented?
Because I restricted to the yes. There are some questions about passage to the limit, which are a little bit subtle. But when I'm in a Noetherian setting, then H and V covers are the same anyways. So, I wanted to find a represented map of Noetherian schemes, maybe. And then it's a cover here if and only if it's an H cover. If and only.
Okay, and what is the descent? So when you have Schrick descent, do you also have star descent, or those are unrelated?
Yeah, that's what I said here, right? So if a Schrick map satisfies Schrick, I mean, the same theorem is true in usual algebraic geometry, or affine schemes. I mean, it's in some special case. So if it satisfies Schrick descent, then it satisfies universal Schrick descent and universal star descent.
This just didn't read it properly. And what is the other statement? What is the meaning of descent for infinite 2 of module categories?
Okay, let me just very briefly do it. I mean, I think this will take a whole other lecture. So some extremely wonderful structure that Jacob Lurie defined in this category of presentable infinity categories was co-limit preserving functors. And in there, you have a subcategory of stable ones, or also, like whenever you work over some ring, you have some categories which are linear over some base category D of A. This itself, so the objects are something like DG categories enriched over D of A's, vaguely speaking, but there's a precise definition of what this means. The functors are co-limit preserving functors. And this has a, well, maybe I don't need it, but I mean, this also has a tensor structure. And now you can also ask the question whether the association that takes such an A or the unspec of it to this infinity 1 or infinity 2 category, actually it doesn't matter which one you choose for this purpose of asking for descent, that this satisfies descent. So by modular categories, I mean objects in this thing, in Jacob Lewis formalism.
So so for example, a derived category of something over A is of some B over A is in this category. Derived category of an A algebra is
right. Yes.
Okay. So you somehow you are giving such things locally, then you are given check descent at least for. Okay. And why is it infinity? So the home between two such things is viewed as itself infinity 1.
Most naturally would be an infinity 1 category. Actually, for this, I mean, you can forget about the non-invertible two morphisms, and then you get an infinity 1 category. And actually, for the question of descent, it turns out it's like the two morphisms, the non-invertible ones will automatically satisfy descent as well. So in some sense, the two categorical structure of this thing doesn't matter so much. And yeah, so right, for these questions, I would really recommend that you read this paper of Akhil Meshew. Which has some awkward title. What is it called? This is a Galopp of stable homotopy. All right. Further questions?
So for the last statement, like from A to the like linear presentable,
Right.
satisfy which type of descent? Like, what does it mean satisfy descent?
Well, I mean, it is a pre-sheet, right? I mean, so you can just, whenever you have a range, you can base change module categories, just you can base change modules, basically. And this pre-sheet should be a sheet. So it's some kind of star descent.
Okay, I see this.
Yeah, so two categories, because star descent is equivalent to one category of sheet descent, which is a bit awkward. All right. Stop.